Hello and welcome to another video. In this video we're going to be going over a number of ways to stay in the same place after some steps. So you have a pointer at index 0 in an array of size array length. At each step you can move one position to the left, one position to the right, or stay in the same place. The pointer should not be placed outside of the array. Given two integer steps in array length, return the number of ways such that your pointer is still at index 0 after steps. Since the answer may be too large, return it modulo 10 to the 9 plus 7. So in this first example, you have an array length 2, and there are 4 ways it looks like to stay at index 0. So you go right, left, then stay, right, left, right. You just stay at one of them, and then you go right and left or right or something, or you stay the whole time. But essentially, what you are basically doing is you are in some array with some indices, and you are just going left and right or staying, and your valid end state is you end up at index 0. And the only things you can't do is if you're at index 0, you can't go left. And if you're at the last index, you can't go right, because you have to stay in bounds. So they say you have to stay in bounds. So essentially, at every location, you have 3 choices, right? Stay, go right, or go left, as long as you're not on the boundaries. And so this is like as simple of a DP problem as it gets. I honestly don't know how this is a hard problem, but regardless, let's go over kind of like why it would be DP and yeah, this stuff for it. So essentially, for DP, you need 3 things as always, right? So you need states, base case, recursive, recursive. And you can recognize it's DP from the constraints. I think the constraints were like 10 to the 6th and 500. So usually your constraints, for DP, usually around n squared, worst case. So that would be 10 6 times 500, which would be like 10 to the 8th, which is passable, I think. Yeah. So anyway, so for the states, we have 2 states, right? We have our index and we have our steps left. So that one should be pretty obvious. For the base case, so the base case is we have 0 steps left, right? So 0 steps left. We need to check what index we are at, and then if we are at index, if it were at 0, then we want to return 1 because that's like one successful path. Otherwise, return 0, right? If we're at some other index, once we've taken all our steps, then we want to return 0 because we want to see the number of ways we can get to 0. And so our recursive case is pretty straightforward again. A, stay, B, move left, C, move right. And you can either handle your logic for checking out of bounds here, or in your recursive case, you can just say, like, if my index is out of bounds, return 0. I'm going to handle it here in the recursive case. So essentially, we're just going to stay, move left if not at index 0, and then move right if not at last index. So essentially, you just add all these up. So you just add up A, B, and C, because these are all of our choices, and return. And that's pretty much it. Then we just do our modding at the end. And that's literally it. So let's code it up, actually. And yeah. And then we're going to talk about some optimizations. So we're going to have mod value that we're going to declare ahead of time. And we're going to have... So you could have a visited, but I'm just going to start using the cache decorator. And this will basically cache the results for you. But you could also have a visited hashtag if you wanted to. But in Python, since this is for you. So we're going to have an index, we're going to have a state steps left. So if the number of steps left is 0, we need to check what index we are at. So if index equals 0, that means we have like a valid path that we took. So we're going to return 1. Otherwise, let's return 0 because we're not at the right place. So now we're going to have our 3 results. So I'm just going to say result equals, this one you can always do, right? You can always just not move. So if you don't move, we're going to stay at the same index, we're going to remove a step. Now we're going to check if index is greater than 0, then we can go left, otherwise we can't. So then we'll add here, we'll add dp of, so if we go left, it's going to be I minus 1, steps minus 1 again. And similarly, if index is not the last one in the array, so if index is less than or rlang plus 1, or minus 1, because like, let's say the array length is 2, the indices would be 0 and 1, so we can move right as long as we are less than 2 minus 1, which would be at index 1. So if we're not at index 1, we can move right. So this is the last index we can be at, and we can't be at this one to move right, so we have to be less than this. So if that's the case, then we will just add that as well. So to go right, we'll do I plus 1, s minus 1. And finally, we will return res modded by this mod because we want to make it smaller. So this cache will handle it for us. If you wanted a visited hash map, you would just declare it here, and this would be one of your states here, and you would cache before returning. I've done that a billion times as well, so either one's fine. And then essentially now all we have to do is return dp of 0 and steps. Because our initial, is that correct? Yeah, so we start at index 0, and we have steps, and every time we take a step, we subtract 1. So let's try that. And let's submit. And you can see it's accepted. So I'll briefly talk about some optimizations. So our time is pretty good. It's about average. But our space could be improved. And so I'll briefly talk about how you could do it, but I'm not going to actually code that up because it's going to be quite long. So essentially, notice once again, when we do our recursive case, our index either goes up 1 or decreases 1 or stays the same. So we only need to store, like when if we did this in bottom-up DP, and we had, let's say our row is index and our column is steps, we only need to keep track of like the index above and the index below, right? So we only need to keep track of a couple of rows. Similarly with steps, we only need the last step. So because we're only relying on like the last step and like the last couple of rows, you can do this in place and you can get rid of one of these dimensions. And so an optimization you can make is figure out like which one of these is smaller, index or steps, and just get rid of that one. And you just use a one-dimensional array and store them in place. And so you could do that if you wanted to, but so basically you'd have to code up a bottom-up solution, figure out which one is smaller. Typically steps is going to be smaller, so you can get rid of steps. I think I is going to be easier to get rid of, but yeah, as you can see with these constraints, typically you're going to want to get rid of, you're going to want to get rid of I and then keep steps, and then that way your space would be a lot smaller, right? So that's how you would make it more efficient. You just code it up and bottom up, get rid of one of these dimensions. And I've done that in a bunch of other videos if you want to take a look. And I think what I will do is make a generic bottom-up video and just point into that, because basically all these how to convert from this to bottom-up is all the same process. It just takes like 20 minutes. So I don't want to do that in like every single video. But yeah, so let's go through the time and space here for our solution. It's still pretty efficient though. So here we have I times steps. So this is going to be like the array length times steps. So technically, actually, there is a thing here that I forgot to mention. So this is not actually going to be array length times steps. In fact, we can even change this. So we can even say array length equals the minimum. Or actually, we can even say array length equals steps, right? Because we can't really get to, like, or actually, no, it would be the minimum, right? It would be the minimum, yeah. So we can actually do this. And this should still pass, and let's just try that really quick. Yeah. So the reason this still works is because, so this actually is not the case. This is still, no, it's not array length times steps. This is more like minimum of array length times steps, and then times steps, right? Yeah, steps never changes, but this one does. And that's because, let's say our array length is like 1,000,000, right? So let's say our array length is 1,000,000, but we can only take 500 steps. Well, even if we go right from 0, like the farthest step we're going to get to is like 500. So it doesn't matter how long our array is. We can only get to, you know, how many steps we have. Like if we just greedily just go right as far as we can never go through everything. So notice this doesn't make our algorithm run actually faster, because what will happen is essentially you're not going to, like, the number of indices you're going to cache, you're not going to cache every single one. Every single one isn't possible. The farthest one you can cache is actually steps. So this isn't really necessary, but this just goes to show that, you know, when you think about your time complexity, it's not array length times steps, it's the minimum of these. So this is actually a lot more efficient than like this looks like, because the steps is 500, this will only be 500. So then it's like 500 squared, which is like fine. And similarly, the space will be the same in our solution. So what would happen if you did get rid of one of these dimensions is you're already kind of getting rid of most of it originally, right, when you do this DP, because you bring a 10 to the 6 down to 500. So then technically you can actually, I guess if you want to then, you can just always get rid of steps in your bottom up, because array length is already going to equal steps, right? So I guess you can save a little bit by like array length could technically be less than steps, but these numbers are so small at that point it doesn't really matter. But yeah, that's how you could make it more efficiently. You could get rid of one of these dimensions, and then your space, if you did that, would be O of like steps or something, or just be actually it would be O of the minimum. If you actually did optimize it enough to get the minimum dimension here, it would be this. So it would be a little bit better, but for the sake of like 20 plus minutes probably, unless you can do bottom up really fast. So not really worth it for me in my opinion. But anyway, so I think we're going to be done with this for now. And yeah, I'll probably make a generic bottom-up solution for a space-optimized bottom-up DP. But this, as you can see, this is still like pretty good. So that's going to be all for this video. And if you did like it, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.